So to start off our class on organic chemistry, one of the things that we're going to have to address first is to get something to know about what is organic chemistry. So first and foremost, it's the study of carbon compounds. We get a little bit more nuanced within that because sometimes we want to reference it as carbon and hydrogen. So for instance, you'll get people referencing diamond is not organic because it's just carbon, or even CO2 runs into this weird kind of gray area because carbon dioxide is coming from an organic source, our living cells, but it doesn't have hydrogen. So the exact definition is a little bit weird. Okay. Add to that, we want to address what those individual components are. So for instance, what is carbon? Okay, so what makes it carbon? How do we identify that? And then after that, well, what is a compound? So we have to be able to have some kind of understanding of those. And once we have that, we can now start to apply that information across. So to start with carbon, we would have to know something about our atomic structures. And that's where we're looking at atoms. And we have our nucleus with our neutrons, our protons, and electrons. And so those are our basic kind of building blocks of how we would put it together. That introduces a whole new set of terms, which in theory you already remember, but perhaps you don't remember some associations with them. Okay? So if we looked at the nucleus, we have protons and neutrons. Well, what is a neutron? What does that define for us? And my argument is that the neutron is really just going to define which isotope you're looking at. Yes, isotopes are based on differing mass for the same element, so both protons and neutrons contribute to that. But once we've defined the element, our protons are static. Our isotope is then going to be dictated based off of our neutrons. And so we can kind of manipulate and divide out our neutrons, protons, and electrons to define certain aspects. Right? So to me, the proton is going to define the element. You change the number of protons, you have a different element. Neutrons are really defining your mass or isotope once you have that element determined. And then on the outside of our atomic structure, we have our electrons, which are really going to define our charge. And just like neutrons and protons contribute to mass, charge is electrons and protons. So it's the blend of both. So when we're talking about organic chemistry, primarily we're talking about our electrons, which is kind of weird because we're ignoring the protons and neutrons. It's not that we're ignoring them, it's that when we're talking about organic chemistry, we're concerned about how one carbon molecule interacts or atom interacts with another atom. That interaction is largely driven based off of electrons to a first approximation, which means we can keep our focus on the electrons and largely ignore the protons and neutrons. They do pop up every so often. For instance, if I go from 6 protons to 7 protons, I now change the identity of the element. Okay? We could also use neutrons to change the isotope for an individual element, which can do something called radiodating or labeling. And that labeling will allow us to look at how a reaction potentially works. So we do see some limited usage, but that tends to be a slightly more advanced class. We don't have to stress too much about our neutrons either. But the big part that's going to become important is where our electrons exist, because those electrons need to start in one place and then change their location. And that's how we're changing the bonds or the connections between those atoms. So if we remember all the way back to Gen Chem, probably our first semester of general chemistry, we had the different energy levels, and we would place our electrons into the lowest energy first, and then we'd start pairing them and all that fun stuff. We still need to have some kind of concept of that, but for the most part, really we just want electrons in the lowest energy, and we want to pair electrons. That's driving our kind of process. When we move up in energy level, the next thing we do have to be aware of is that we don't have the same types of locations. So the first energy level is different from the second, but not just in differences of energy, but also the different types of orbitals or the types of places that you can put electrons. This is where we introduce the concept of S and P. So every time we move up in energy level, we get a new type of orbital to appear. And we could do this forever. So we go all the way up to the 7th energy level, we get 7 different types of orbitals, and that's really complicated. Organic chemists don't like things that are complicated, or rather, we focus so much on the things, relatively simple things, that if we tried to go too far up, it would just destroy our brains. So we keep our focus relatively low, and we really only focus at those lower energy levels, right? Which means we really only have to worry about S and P type orbitals, and we can largely ignore the D. When we're looking at those, we do have to have some understanding of what those orbitals mean. So we get shapes associated with those. Those shapes are probabilities. Then yes, we're going to have to dig into those probabilities and come up with some understanding of what's going on with those. But we do have to know what these shapes are and what it would mean, because I'm now taking 2 molecules and bringing them near each other. If I looked at a sphere, if both of those were spheres, well, they're now going to interact on the outside of that sphere. That kind of makes sense. But if I had dumbbells, okay, with my thumb being dumbbell pointed up, and I brought them near each other, well, I'm going to have to get a whole lot closer for them to actually interact, because the orbitals are on a different plane. If we take the dumbbells and turn them this way, the interaction happens at a larger distance. So we have to take that into consideration, because a lot of this is spatial orientation. So when we're thinking about these objects, we have to think about it in 3 dimensions. And right now, all we're saying is just on that one axis, okay? But it could happen on this axis. And you're like, well, what the hell are you doing? And exactly, you have to shift your focus to recognize that that same spatial representation on that x-axis or y-axis, whatever you want to call it, could happen on any axis, and that makes it more difficult to see what's happening. Okay? So we have to be thinking about things in 3 dimensions, and that will become more and more challenging. As we continue on, we could go through and explode out and look at our entire periodic table. But again, we want to simplify things. The point is to boil this down, keep our focus on carbon, because it's the primary driver of a lot of these reactions, and zero in. That means we get rid of a large percentage of our periodic table. And so what you're seeing here is what you'll see for each of your exams. We don't need the whole periodic table, we just need pieces of it. Okay? Add to that I would argue a lot of these pieces we just don't see in organic chemistry. So to me, we'd simplify it further. So now what we're looking at is really just a handful, or really 2 handfuls of elements, and we can now kind of drill in super deep to look at just those handfuls and extrapolate out to the rest. Okay? There are some cases where we'll encounter other elements. For instance, sulfur does show up every so often, but for the most part, we keep our focus within these. Okay? The next thing that we have to pull back from our Gen Chem knowledge is the patterns that are found in the periodic table. We may have eliminated the vast majority of the periodic table here, but the patterns underlying the whole thing still apply. So what were those patterns that you should have remembered from first semester general chemistry? Well, I would argue the things that I would pull out of this have to do something about those ever important electrons. So for me, what are those electrons? Well, I know these first 2 sections are known as the s block orbitals, because the s block involve those s orbitals, and these would be the p block orbitals. So those are involving p orbitals. This gives me some information about where I place the electrons, okay, and what type of orbitals. The next thing that I might like to reference within this is that these are energy levels. As we move down, we're increasing in energy, which means we get larger, okay, down the periodic table. So our size becomes important. Okay, so down a column, we get bigger. Well, then we should also be thinking about what's happening in size as we move left to right, or rather, right to left. We also get larger. That one becomes a little bit trickier to acknowledge. Okay, so take a second and see if you can come up with a solid explanation for why we get larger going right to left. And yeah, this would be one of those times that you'll hear periodically throughout these videos saying you need to pause and think about what's happening and what we're talking about. Why does it get larger from right to left? Okay, so hopefully we've had a second there. And usually what I'll hear people say is that it gets smaller left to right. Okay, that's fine. You're explaining that same trend, and you're saying it gets smaller because there's more protons. Okay, and this is tricky. You're correct. Fluorine has more protons than does lithium. And so let's push that. If that's really the case and that's the rule you're going to run with, should potassium be larger or smaller than lithium? Well, there lies a problem because potassium has more protons than lithium. Okay, so it's not a question of which element has more protons, because that doesn't answer the question. Okay? What we need to be addressing is a little bit more involved. Okay? And it's so much more involved that we're actually going to simplify our arguments significantly when we move left to right. And so I'm going to erase that arrow and focus on our bigger issue here. So down a column, yes, it gets bigger. Why does it get bigger? Okay, well, size is due to electrons. The protons are in a tiny little nucleus, so those are irrelevant. Our electrons are on the outside. As we go down a column, it gets larger. Is that because we have more electrons? Well, left to right, we have more electrons, and we aren't changing the size, at least in that same trend. So there has to be some other reason to it. Well, that other reason has to do with the numbers that we started out with. It's our energy levels. When we go down a column, we get larger because our electrons are going into higher energy levels. The energy levels represent a radius. The larger the atom is, that means your electron is going into your outermost electron is going into the highest energy level possible. That's why it's getting bigger. So how would we extrapolate that rule to our left to right, our rows now, our period? Well, left to right, they're going into the exact same energy level. Well, if our electrons go into the same energy level, what should happen to the radius? Nothing. Nothing should happen to the radius. And when it comes to ochem, the radius change left to right is so minuscule that we can ignore it. So when we're talking about size left to right, there's no difference. Okay, and this becomes important because when we're evaluating reactivity, size is a big part of it, but there's another part that's going to become important, and we'll look at that in a second. Okay, so what I want you to remember with size, down a column, bigger. Across a row, no difference. Okay? For those of you that are like, but I remember there was a difference, well, you need to come up with a better explanation. And in fact, I would argue that that's a pretty good first week question that you could post to our discussion board to explain why size does indeed change left to right. Okay? So for our purposes, again, just want to be extra clear, size does not change left to right. Okay? The next thing that we should throw into this that we need to remember would be that fluorine is the most electronegative. So we get an electronegativity trend. Okay, and this becomes important because our electronegativity is the ability to steal electrons from another atom. And if I'm looking at how two atoms interact, well, electronegativity is going to dictate that. Okay, so we need to be familiar with our electronegativity and our size because those two things are going to dictate how our reactions work. Okay, so let's go ahead and summarize that all because I know there was a lot. There's a little bit of conflicting information there. We need to know where our orbitals are, so we get our S block and our P block. We need to know something about size. And when it comes to size, down a column, bigger, that's it. Electronegativity, left to right, more electronegative. Okay, that simplifies things a lot, and that can help us in those kind of weird cases when we're thinking about reactivity on how those things come together. So try and remember those. The next thing, Now we're going to bring these atoms together to form these compounds. Well, when we bring two atoms together, we get some kind of interaction. Okay? The result of that interaction is going to dictate whether we see a chemical reaction or whether we see nothing, okay? Or potentially even a physical interaction. The things that are going to control that are going to be how those electrons are held on each individual atom. And if one atom wants to steal electrons from the other, we could change those interactions. So what we're thinking about is this big spectrum of possibilities of no interaction to holy crap, they're now sharing electrons. So a really strong attraction. And so those electrons are really going to contribute there. And that's going to be the important part, which is why we need to know where our electrons exist. If we boil down that interaction, we're really going to get two options in my mind. We get a strong attraction, which we're going to call a bond, and we get a weak attraction, which we're going to call not a bond. That's a stupid name, isn't it? So let's call it something fancier than not a bond. We'll call it a force. Okay? So you need to remember back from Gen Chem what qualifies as a bond and what qualifies as not a bond. Okay? So bonds and forces. Intramolecular, meaning between or within a molecule, are our bonds. So if two atoms are held close enough to each other that they become a molecule, now we're looking at a bond. Intermolecular means between two different molecules. How are those molecules interacting with each other? They aren't formally making a bond, they're forces. Okay? They're that not bond category. Bonds, we're sharing electrons. Forces, not sharing electrons. How do you know what bonds there are? Well, hopefully you remember three of them. Yep, ionic, good guessing, keep going. Polar covalent and nonpolar covalent. The nonpolar covalent I put in parentheses because I don't like saying nonpolar covalent and just call it covalent. Okay, so how do you know you have an ionic bond? How do you know you have a polar covalent bond? How do you know you have a nonpolar covalent bond? The rules behind those go strictly based off of differences in electronegativity because nobody's got time to memorize electronegativities. That's not true, you probably do. We probably want some kind of rule of thumb. So there are some useful rules of thumb. Ionic, metal and a nonmetal. This is going to become important because if we went through and looked at, say, chloride, you might go, well, that's going to be ionic. And you say, well, why is chloride ionic? Well, you see the charge. So seeing charge is a dead giveaway that it's ionic. Right? It's such a dead giveaway that we typically don't show it, particularly in an exam, because if we did that, you go, oh, it's ionic. So we do this. And now for those of you being like, well, it's still ionic, okay, good. You won't be tricked by that question later on when it shows up on an exam. Okay, very easy to now lose track that this is still an ionic compound. Okay, and what happened is you overemphasize the charge and you ignored the fact that this is a metal. And because that is a metal, we now have an ionic compound, and this would be represented as Na+ and Cl-. There's the ionic interaction. Okay, so don't forget these kind of basic principles because they come into play a lot. Polar covalent, I'm going to skip because I would argue the polar covalent is a hard one to deal with. Non-polar covalent is a little bit easier. There's really two categories, same to same. So if I take a carbon and bond it to a carbon, well, that's a non-polar covalent bond. And carbon to hydrogen. So I can throw in a hydrogen on that. Each of those bonds is a non-polar covalent bond because they satisfy that rule. Okay? I could throw on chloride. Okay? And chloride, you might say, well, chloride to carbon, okay, that's not same to same, so that's not a non-polar covalent bond. But if I did chloride to chloride, that's a non-polar covalent bond, okay, because that's same to same. So we're kind of ignoring the electronegativities for the moment, because really we're just saying same to same, non-polar covalent, and then our ionic, the differences are so large, that's why we're saying metals and nonmetals. Where does that leave us for our polar covalent? Well, that means our polar covalent is really left with everything else. And this is why that definition becomes difficult to deal with, is that if you try and use the everything else definition first, you can't really apply everything else. So when you're looking at this, it's ionic, nonpolar covalent, then polar covalent as your definition categories. Okay? You might again be freaking out and be like, well, there's so much on the periodic table. How could I possibly remember that? Remember, we only have 10 elements. Okay? Organic chemistry has simplified this down so that that everything else category is relatively narrow. So when you look at a compound, okay, the combination of at least 2 elements, you should be able to quickly identify these bond categories. Those bond categories become helpful because they can explain something about the reactivity. If I see a nonpolar covalent bond, well, how do I know something about its reactivity? Well, that reactivity shifts from bonds now into forces. And when we shift over into the forces, we would now have to name those forces. Hopefully you also remember the names of your forces. Ah, good for shouting it out. I like that. And you even use the word electrostatic, because electrostatic we're trying to differentiate from ionic bond. An electrostatic force is really just an ionic force, but ionic in both those cases becomes confusing. Okay, hold up. Yep, I heard you. London dispersion forces. And I also heard induced dipole, which is fantastic. That is also a London dispersion force, or just dispersion forces. There's tons of names for that category. Really, probably the best one is the induced dipole, which is just a mouthful to say. So what you'll see me reference these as is LDF, or London dispersion forces, just to kind of simplify that. I did hear someone shout hydrogen bonding, and I appreciate that, but no, I'm not calling that a force. And we'll address that later, so don't stress. Dipole. Good. So we have really 3 forces: electrostatic, dipole, and London dispersion. You should also be able to quickly identify which of these forces are present. And really, we do that by identifying the bond that allowed them to exist. So polar covalent bonds will generate dipole forces. Electrostatic forces come from ionic bonds, and our London dispersion forces come from nonpolar covalent bonds. And if we think about these, why these become important is that we can look at a strength behind these. The electrostatic force is very strong. The London dispersion is very weak. What does that mean for us? Well, if I have a nonpolar covalent compound, what might I predict about its reactivity? Well, its reactivity means it has to interact with another molecule. It's a weak interaction. Nonpolar covalent bonds, I can effectively ignore when it comes to reactivity. Whereas those electrostatic forces are now going to generate strong interactions. Okay? So if I have some kind of understanding behind these bonds and forces, I can predict something about how they would react. Okay? I would argue this all comes in together, and really this diagram I still haven't updated, but we've got a continuous spectrum, okay, that are bonds and forces, and we kind of cut that spectrum in half and said on this side they're bonds and on this side they're forces. Well, then what I did is just take that bar and turned it into a circle, and now we can see the relationship between our bonds and our forces. A polar covalent bond, say in this green color, is going to match a dipole force in that green color. Okay? So at this point, we'd ask, are there any questions? And someone, yeah, that was you, yeah, good job, says, you said just a few seconds ago, maybe minutes, hydrogen bonding wasn't a force. And yet, because you have a very good observant eye, hydrogen bonding is listed on my forces. And yes, hydrogen bonding is a force. One of the reasons why I don't include it when we initially start talking about forces is that students will overuse it. Hydrogen bonding is a very special case of a dipole-dipole interaction. So you need to make sure you have a dipole-dipole before you start talking about hydrogen bonding. If you don't have the dipole-dipole, you don't have hydrogen bonding. Okay? The nuancing behind those is in a separate video, and we will talk about it again when we start applying these intermolecular forces and bonds to particular physical observations. Again, different video. If you need help remembering what's ionic, what's polar covalent, all of that, that's what that intermolecular video or intermolecular forces video is for. Right? It is real base level to try and establish those relationships. If you don't understand those, you better freaking watch it so that when we start talking about the application of them, you're good to go. Okay? And with that, what was supposed to be like a 10 to 15 minute video, we've got 25 minutes, but we've kind of covered everything that we're really going to address. Okay? First level. We'll then start to push deeper a little bit later. Okay? And in fact, probably this next video if you're going to watch that.